Alrighty, hey guys, we're going to go ahead and get started now. Thanks for coming on a Friday. Really appreciate it. Okay, cool. So first off, we'd just like to thank our sponsors. They let us run these events, and they're pretty cool. So our gold sponsors are Potentia, FNZ, and Centrality. And our silver sponsors are Serato, Zero, Optiva, Atlassian, and Nintex. Kind of a quick agenda for what we're going to be doing tonight. So this is the DEVS Game AI Workshop. So first off, we're going to start off with some demos of what we're going to build tonight, kind of get everyone a little bit excited. And then we're going to go into a little bit of theory about brains, AI, neural networks, all of that sort of stuff. And then we're going to talk about genetic algorithms, which is how you train your neural networks. And then we're going to look at a couple more examples at the end. So Ben is now going to start us off with a couple of demos. And yep, you go, Ben.
Cool, yeah. So thanks, guys, for coming along on a Friday night. Possibly got more exciting things to do, but I think this will be pretty fun. So let's first go through how today is going to work. So what we have, get this set up. So we've set up a Google Colab notebook for you guys. So if you don't know what that is, it is kind of an online environment where you can run code, so you don't have to download anything on your computer. It's all in the browser. So if you want to find your way to this notebook, you can use these links here. So we kind of have two versions. So we've got a version with all of the code filled in, so you can kind of just follow along, run it, see what it outputs. But we've got a more interactive version here, which is kind of a fill-in-the-blanks type thing. So you can follow along. You'll actually be doing the coding. You can change things up how you like, and it's a bit more interactive. So that is bit.ly/devsai blank for the blank fill-in-the-blanks one, which I'd recommend. And then the answers are here, just devs AI. We also have a GitHub repository with just all of the source code that you can look at. That one, you have to set up Python, download dependencies and stuff. So it's a little bit less usable. So we'd recommend following along with this collab. Let's give everyone a few seconds to set up there. Yeah, and just /devsai blank if you forget it. Cool, and if you guys have any issues setting things up, you can put your hand up and Liam will come help, or some of the other devs guys. Cool, okay, now that people should be set up, let's go on to what we're working with. So today, we're going to be training an AI to play games for us. So the game we've chosen is kind of a simple game of Pong. Hopefully everybody knows what Pong is. But if you don't, what we're going to do is just have a little demo. So I'm going to need 2 volunteers for this one. Just come up and show us what Pong is. We are going to be playing against each other, and the winner will win a hoodie. If that's anyone want to come up? Yep. So that's one. And anyone else? Yep. Cool. So yeah, we got our players here. So it's a competitive game. So one of you, so Pong's got the 2 paddles, right? So one of you needs to be on the arrow keys, move up and down. Okay. One of you on W and S. So give you just a little test run first to get come on. So here you go. We're playing. So yeah, just arrow keys. Yeah, so you're on the left, you're on the right. Oh. And you've kind of got little life points in these red numbers here. So this is it's difficult, but we need someone to win.
Yes. You're going down.
The most competitive Pong game I've seen.
Ooh.
Oh.
Wait, what?
Yeah, so you lose health depending on how much you miss it. So, you guys want to go? That was a test run.
Okay.
Okay. Where have you episode?
Round 2.
Wait, what?
So this is what we're making. So instead of human players, we're going to have AI playing instead.
This is quite a fun game.
Oh.
Ooh.
think this is going to be the next Olympic sport.
Yes, of
Oh,
course.
right.
You need skateboarding and you have poles.
Oh.
Okay, so you are our new hoodie winner. Talk to the dev guys after this. So you're out.
Cheers.
Cool, thank you guys.
Much appreciated.
So that's what we're going to be making, little Pong game. So that was human players, obviously, but let's have a look at some AI players. So this is me playing on the right, and the AI is on the left. So this is for us comp sci students who don't have friends. We can just play Pong by ourselves against the AI. And I think I'm worse than you two because I'm going to lose this one. So let's cancel that before I lose. So that's what we're going to be making. So how we've set this up is that we have a little bit of helper code. So the helper code's all pure Python, no libraries or anything like that. If you're interested, you can have a look. It's on the GitHub repository, and we just kind of import it into our Colab notebook here. So there's a few interesting things there. But all the kind of the real stuff that we'll be going through, the neurons and neural networks, we'll be teaching you all the Python code of how that works, and you'll be coding it yourself. So I'm going to bring Liam back up to teach you guys a little bit about the basics of how our brains work and how we actually learn things and how we can train an AI to do that.
Alrighty. Cool, thanks guys. I'm going to sit down just because I'm very tall and the mic's very low. So if any of you have any trouble with the Google Colab, just raise your hand. You kind of have to, if you want to run the individual cells, you can just come down here and they've got like a little play button. You'll have to connect first. So it's cool because it basically gives you like a virtual server to run all of your AI experiments on, which is nice. Yep, so, sorry? Oh, do we have to?
Get him to hit install dependencies
Yeah.
as well.
Yeah, so please you have to like trust the code and everything. So the dependencies might take a second to install, so we recommend doing that while I run through a bit of theory to start off with. Okay, so yep, we're going to be talking about brains, AI, and neural networks. This is essentially the brunt of our theory here. So human brains. When you're playing the game Pong, your brain kind of goes through this loop. So you're going to observe the state of the game. So this might be like where the ball is, where your paddle currently is, what's the speed of the ball, all those sorts of things. And then observation gets passed to your brain as an input. Your brain processes the input and creates some output. And then you perform some action based on this output. So most of the time that's just moving your finger to press the up button or the down button. More complicated games, it's a more complicated action. And then after that, the game state updates based on your action. So your paddle moves up or down. And I do apologize if there's any biologists here. These are gross oversimplifications, but it makes it easier to program. So we're going to assume all of this is true. Yeah, so it seems pretty simple, right? You've got observations, processing, and output. So how the brain actually processes the information is quite interesting. So you have those sensors at the beginning. So these are your eyes, your ears, maybe your fingers, like which button you're currently touching at the moment. And your eyes and your ears will translate these into electrical signals, which are then transmitted to the brain via your nerves. So once it's in the brain, these signals are processed using special cells called neurons. So these are natural cells in your brain, but we're going to try and replicate them with computers in a little bit. So these neurons output a new signal, and then, as mentioned before, these signals travel to your muscles, and you do some action based on that. Okay, so the neurons, this is kind of what a neuron looks over here. Looks like kind of gross and stuff. I don't know, I don't do biology, but we're going to try and emulate some of these guys. So neurons take in multiple inputs and combine them to make one single output. So your brain is just an entire network of these connected neurons. So you have one neuron that then feeds its output as the input into another neuron, and this is repeated over and over and over again. So the layers of these neurons are all connected together, and the signals then flow between the neurons. So they get combined, emitted repeatedly over and over. So the final neuron layer produces some output, which is then the signal to your muscles to perform the action. So it's not as simple as just having one neuron. There's a whole bunch of them that are kind of combined into a network. So how do we emulate this in a computer? So our artificial neurons are pretty simple. We make a lot of assumptions here, but We try and replicate it using a system where we have n inputs. So these are those ones over here. And these are just numbers. And then each input is assigned a weight for each number. So that's kind of like the strength of the input. And then the neuron itself has a strength bias. So that's basically how strong of an influence that neuron will have on the outputs. And then it spits out an output. So the calculation is very simple. It's just a little bit of mathematics. You take each input, multiply it by the weight, do that for all of the inputs, all of the weights, and then you just add your bias. So for the example here, 1 times 3, there, 1 times 3, 1.5 times 2, and 2 times 1 plus 4, which is the bias there, and you get an output of 12. So for the neural networks, as I mentioned earlier, you kind of have layers of these. So you can see here we've got like 2 distinct layers of neural networks here. So you've got some input all the way here on the left. It becomes the input into these neurons, which then output something, which then becomes the input into another layer of neurons. So you've kind of got an entire stack of these layers. So to break it down, you've got an input, 3, 2, 1. And then so neuron 1 and neuron 2 are the 2 neurons in the first layer. You can have any number of neurons in here. The ones we've chosen for our Pong model are kind of optimized for the problem, but you can play around with it if you want. And then so N1 has certain weights, and this is the same example from beforehand, so it'll spit out 12 when you perform this calculation. And then we're just assuming that N2 has some weights and some numbers in here, and it spits out a number like 18. So what happens next then is these numbers, 12 and 18, become the inputs into the next layer. So you can see here that this layer has 3 neurons, but only 2 inputs. So it's a slightly different structure. And then, so they all calculate their number, and then this comes out into an output. So we've got 3 different outputs here. So for Pong, this translates to move up, stay where you are, and move down. And we'll explain more how we select that in a second. So when coding up a neuron, we have to ask ourselves what are the properties that we need. So we need the inputs, the weights, the biases, and the output. So this is a diagram from earlier. Ooh, okay, that was meant to be the other way around. That's all good. So we're going to jump over to our Google Colab now, and we're going to implement our first neuron. So those are the fields that we need to implement, and these are the functions down here. So when we come and have a look at the Colab, you're going to want to scroll down to the, here we go. So the Colab document also has a lot of the theory, so you can actually work through the document afterwards without the slides if you want. But here we go. So you're going to want to come down to the section, an artificial brain, and then let's implement this in code. So how this is kind of structured for the fill in the blanks is we'll give you a little bit of time to go through, and then it's most of the time it's just a one-liner at the beginning here. So it says what you need to do, and if you just kind of add in a little bit of code there, I'll give you a couple of minutes just to try that, and then I'll code up an example. What I'll do now is I'll just quickly go through and code up an example for how we want to implement our neuron in code. Yeah, 1 sec, sorry, I'm just trying to stack the laptops there.
Screens.
Too many screens. Okay, so over here, in our function to add a connection to the neuron, what we want to do is we have this connection weights property on the class. So we can just do connection weights dot append weight. So this is just going to push the weight onto the list of weights that we're maintaining. For the next one, for this self set bias, so we can just self.bias. Self.bias is bias. And then for the last one, we do have another one here. Okay. Perfect. So we're going to set it to 0 first, and then we're going to use a little bit of Python trickery here to do this nice and easily. So I'll explain this in a second.
Possibly zoom in on that one.
Yeah, sorry about that, guys. I'll zoom in a little bit. If you had issue reading any of that, just raise your hand and we'll give you a hand with that. Otherwise, there was that answers document. So if you do find you're getting lost, feel free to just jump on that, copy and paste the code a little bit. Okay, cool. So we can also ignore this code down the bottom. This is just for saving and restoring our model, which we'll use a little bit later. Okay, cool. So we've now got a neuron, and so we can, when you set up the neuron, you have to give it a bias, and you can add a whole bunch of connections there. But what we can do is we can actually make sure that it's correct, which it's not. What's going on here? Plus equals input times weight. What do? This is the problem with live demos.
Copy and paste it.
Do you have the other one open? Okay, this is why it's nice to have a example one. I might actually just keep the example one over. Sorry?
Oh, you didn't do that one. You have to add the bias.
Ah, yeah. Okay, good catch. All right, cool. Now the code's working. So we have some nice helper code to be able to display these neurons. So these are kind of the graphs from earlier. So we can show what it looks like. It generates these cool little diagrams here. So you can see the calculations being performed. And if we go back in our slides, that was actually the same calculation being performed there. You can check the math, but it's all correct. And then the other thing we can do as well now, so there's another coding challenge here. So if we can figure out how to make this neuron output 18. So in the example we had over here, neuron number 2 was outputting 18. We know the inputs, we know the output, but how can we mess around with the weights in order to make sure that it outputs 18? I'll give you guys a minute or so to kind of try that one out. Alrighty, I'm going to start filling in some of these values. I have the advantage of already having the answers, so I don't have to do any math in my head. But what we can do is we can have a look at how this works. So it's 2, 3, 2, 3. Perfect. And then we can see that our neuron here has outputted the correct answer of 18. Can I get a quick show of hands if you're still struggling with any of the codes so far? I can slow down, otherwise I'm going to keep going. Okay, cool. I'm going to keep going. Yeah, so this is quite cool because we can essentially, via some optimization, we can adjust the parameters to get some desired output. So if we know our input and we know our output, we can kind of play around with the weights and the biases in order to get some output. And so these are called the parameters of our neural network. So a very simple neural network of just one neuron just has 4 parameters. You've got those weights and you've got the bias. But a more complicated neural network has all of the weights here, all of the biases on all of the neurons, and then all of the weights in between each of the layers. So trying to guess that is very easy for one neuron, but it gets complicated very quickly for multiple neurons. So yeah, we're normally given the inputs and must return an output. So for Pong, you're given the state of the game, and you're expected to produce some kind of move, and you need to figure out how to get from the input to the output. So if we tweak the parameters, we can try and perform the correct action, and then when we select the output, we select the largest neuron output. So in the example here, we've got these 2 outputs of 12 and 18. If this were the final layer, we would select number 18 as our output. Okay, cool. So now I'll just quickly explain how we get the inputs from the Pong game. So kind of got a bit of a diagram here, and it looks all right on the board, which is nice. So you receive input as just like an array of these numbers here. So what this translates to basically is the distance the ball is away from your character, the height of the paddle, the height of the ball's x direction and y direction, so it's kind of like its speed. So here, if the x direction is 1 and the y direction is 0, it's actually just moving sideways directly at you. So in this particular example here, the logical move, if you were a human, would be to try and move down to block the ball. And that's what we're trying to replicate with our neural network. We're trying to have it so that it makes the correct decision that given this output here, it should spit out the largest number on the bottom, which means we move down. So you can see this is the actual trained network we saw earlier. So this one's a lot more complicated than the ones we've seen previously. So you probably wouldn't be able to guess this by hand. So as I explained earlier, so the top output stands for move up, the middle one is stay still, and the bottom one is to move down. So if this was a good AI, a good neural network, we would expect the largest output to be down the bottom here so that it would move down to try and stop the ball. So now we can code up a neural network. So essentially, we want to create a neural network that starts with neurons that have completely random weights and biases. So this is kind of like an audience interaction thing. We'll see how this goes. So what are some of the properties that we'd probably need if we wanted to code this up? Just feel free to chuck up a hand if you have any idea. Yeah?
Instantiate an array of neurons with different natural weights.
Yeah? Is there actually anything else? I think that's basically it. Yeah. So tiny little bit more. Don't worry about this. We'll get to that in the next section. So yeah, as you mentioned over there, so essentially just need to keep track of all the neurons. We need to keep track of the layers as well, like the shape of this. So you can see this one's very differently shaped to our previous networks. It's got 5 inputs, 3 outputs, and the layers here have different numbers in them. So we need some way of keeping track of that. And we need some way to get the output of the neural network. So given some input, what are the 3 numbers that we're going to get out here? And finally, we're going to give it a fitness field, but we won't worry about that yet. We'll deal with that when we come to the genetic algorithms section in a little bit. So now if we come over to the code, we're actually going to code up our neural network. So is this? Oh yeah, perfect. So here there's a couple of different sections that you have to fill in. So be aware there's 2. Yeah, there's 2 sections here that need to be filled in. So I'll give you a minute or 2 just to get started on that. Then I'll start coding one up.
If we just explain what the 2 sections are. So this bit's filling in the layers, and the next bit's getting the output.
Yeah, perfect. All right, so I'll kind of just go over the comments as well, just to explain what's going on here. So this one in here, we're going to be setting up all our neurons and giving them those random biases and weights, as we talked about earlier. So it'll become apparent in a little bit why we're selecting random values for these. But for now, we'll just go ahead and implement that. And then down the bottom here, this is where we're calculating our output. So we want to be able to perform those calculations from earlier, these ones here. But we want to be able to do that for every single layer in the neural network, and then we want to be able to output some final values. For any of the random numbers, we're using some code that will look like this. So NP is NumPy, which is the random number generator for Python. So you can just go ahead and copy that basically just to generate any random numbers you need. Alrighty, and then I'll go ahead and start implementing it now. Once again, raise your hand if you're getting a little bit behind and I can slow down. All right, so I'm just starting off my for loop there. So we want to kind of iterate through all of the neurons in the current layer. Neurons. And then we're using our neuron class from before that we made. So we can just do something like that. And then, so we also need to set our bias. As previously mentioned, we're going to be using random biases to start off with. Okay, so that's using the bit of code from up here, which just generates a random number between -1 and 1. And then finally, we need to... okay, yeah. So we need to come through and do this. So
That line's open.
oh yes, no, you.
Just leave it. So this is just setting the weights.
Okay, so we're just going through and we're setting all the weights for the neurons. So
I mentioned that you need a weight for like everything on the previous slide.
yeah, okay. I'll cover that in a second. That's good catch. Oh my god. I think I might just start using the neuron layer. Neuron. Okay, so a quick point as well that you want to keep in mind is, that's not a great example there. We'll go back to the previous neural network. So one of the things that might not be immediately obvious is that for each of our inputs, we need a weight associated with it. So that's what our code here was doing as well. So we have all the previous layer is just the inputs into the current layer. So we had to go and create a weight for each of them, and then we had to add the connection as well. So it's very important that you make sure you get the correct number of weights and inputs. Okay. Someone's got a question for which button do you push? So on the, I assume they're meaning on the Google Colabs. What you want to do for that is just on the side here of any of the code, they have this little play button. You can also press Control-Enter if you'd like. Alrighty, guys. So we're going to go ahead and try and run our neuron code now. So this is our very first neural network. Yeah. So we can see that when we give it some inputs here, then it's going to generate some outputs for us, as expected. And then we can also just show this neural network here. What's going on? Show networks undefined. Apologies for the minor technical difficulties. Oh, did I skip one?
Yeah, we skipped the first one, so kind of skipped. I'll just run them all anyway.
Yeah. Okay, cool. So we can see here that this is the same input that we get for the Pong. So we've given it the same input here. So it's the same hypothetical game situation right over here, but we're actually getting a very different output. Its highest output is on the middle here. So it's actually saying that we should stay in the same spot, which is not a great move, considering then we'll lose some health and probably lose the game because it's going to the ball is just going to go straight there. So obviously this is not a great initial neural network. Yeah. So it doesn't appear to be very good. Selecting the random weights, I told you we'd learn a little bit more about why we're doing that. So obviously they're not the best choices. We can be more intelligent about that. And we can actually teach the neural network how to produce the correct outputs. So we can go from some bad neural network to something that's much better that will actually perform like we were seeing earlier. And in order to do that, we're going to be using some genetic algorithms, which Ben will be running you through now.
Cool. Yeah, so I'm back to talk about genetic algorithms. So let's have a little brief recap of what we've looked at so far. So we're playing the game Pong, and in this game, we're given kind of this is called an observation. That's kind of our view of the world. You can imagine it like our AI is kind of looking at the screen, and this is the information it's getting back. And this information here is shown here as kind of a list of numbers. That's just being passed into our AI's brain, which is this middle section here. So the brain, kind of, you can think of it as just processing numbers. So we start off with numbers. Those numbers are getting shuffled around, added together somehow, and ending up with some outputs at the end. And somehow, magically, these outputs at the end kind of correspond to correct actions which play the game. So the issue that we just ran into here is that some brains, so this one on the left, are producing kind of the wrong output. So given one input, they're giving us the wrong action. They're telling us to play the wrong game. Whereas some brains, this one on the right, are giving us the right output. So the one we just saw was telling us to stay in the middle when the ball was coming down the bottom, whereas a good brain would tell us to move down. So you can see that these things kind of look similar. They both have the same structure. The brain kind of looks the same. The only difference is kind of these neurons in the middle have different values. They have different properties. So the problem kind of we're trying to solve here when we're learning is that we want to find a brain that's good. We want to find a brain where all the numbers kind of add together to give us the right output. And the way we do that is we're going to take inspiration from nature. So nature does this by evolution. So kind of think back in the start of the world, right? We just had bacteria going around, and they're just kind of moving around randomly. Some of those bacteria somehow perform well, and they kind of survive, whereas the bacteria that don't perform well die off. And over time, over millions of years, those ones that perform slightly better will live longer, produce more offspring, and through evolution, we come to where we are today, where these animals kind of perform really well. So we're going to try and do the same thing here with neural networks. We're going to take these bad neural networks that we have. We're kind of going to test them, see how well they do, and we're going to throw away the ones that do badly, keep the ones that do well, and just kind of keep that process going for generation after generation until we end up with good neural networks. That's kind of a brief overview. Let's look at how we're actually going to do that. So again, going over the theory. If we look at this a little bit more as we would in code, we'd start off with some random population. So we're going to create a whole bunch of different random neural networks. We're just going to assign numbers randomly, which is what we just did with Liam. We created a neural network with random numbers. We're going to check how well each of those kind of AI brains does at playing Pong. So we're going to play the game, see how well they do with the score, and assign that as what's called a fitness. So this is kind of a value that's measuring how well they do. And then we're going to create a new population based on that. So we're going to keep the neural networks that do well, throw away the ones that do badly, and just repeat that process over and over. So first, let's start with the easy part. We just need to create a population of neural networks. So no, I'm going to go through the fit theory first. So this is kind of just a whole bunch of neural networks. They're all going to be random, and they're all going to have different weights and biases. So we can think of these as kind of like the DNA in animals. So DNA, just a whole bunch of numbers. Our neural networks, they just have a whole bunch of numbers as well. So we're going to start off with random parameters, and they're going to improve over time. So let's have a look at this fitness thing. So it's just how good our neural networks are. So if we think about the animal world, back in high school biology, you might have seen pictures like this. So each kind of animal has a niche that it has in the environment. So it learns to perform really well at that niche, and that's kind of its fitness. So here we have this butterfly that's kind of trained itself to be really good at camouflaging itself like a leaf. So its fitness score would be how hard is it to detect compared to other leaves. And we're going to try and do the same thing with a neural network, but how well it can play Pong. And then once we have these fitness scores, we are going to use them to kind of pick our new generation. So the members that do well are going to survive. The members that don't do well are going to die off, just like in the animal kingdom, I guess. And we're going to think about our DNA as just these random parameters that our neural networks have. And we're going to think about creating children from those. So we're going to take two good neural networks that have good sets of numbers. We're going to combine those together and create kind of children neural networks that take properties from both of them. So the problem with just that system is that we're never introducing anything new, right? So if we have one parent neural network that knows how to move down, we have another parent that knows how to move up, we can combine those into a child neural network that can move up and down, which is what we want. But if we just have neural networks that only know how to move up, they'll never learn to move down just by combining them. So we need to introduce mutations into our DNA. So again, this is kind of inspired by the real world, but we're just going to change our numbers a little bit every generation. So we're going to take a good neural network that knows how to play Pong quite well, and we're just going to change some of its numbers a little bit. Maybe that will make it better, maybe that will make it worse. And over time, over hundreds of generations of these things, we'll end up with neural networks with good mutations that work well. So here is a little GIF of our good Pong players, and most of them aren't going to be this good. So this is kind of a best case scenario, but most of the initial ones that we train, they're just random, so they're going to do badly. They'll get horrible scores when we play them, and they'll die off. But we're going to keep around the good ones that kind of play like this. They'll produce children. Those children will also be good, and will slightly get better over time. Cool, so that was a real quick run through genetic biology, which any biologist probably cringe at. But does anyone have any questions about that? I've all done high school biology, kind of know how evolution works. Cool. So how do we actually implement this in code is the tricky part. So the first thing that we need to do is create a population of neural networks. So with Liam, we just looked at how we can code up a random neural network. So we're going to start off by just creating a group of these random neural networks. You can think maybe just a list with 100 random ones. So let's jump back over to the Google Colab and scroll down to this cell here. We're just going to create a population class which is going to contain our population of neural networks. So you can see we have some parameters here. We have kind of node count, which is the shape of the neural networks we want. We have population count, which is going to be how many is in our population, and some mutation rate, which we're going to look at later. So for your code, what you have to do is just initialize this variable here, this population variable, to be a list of neural networks. So we should have population count of them and just a list holding those. So I'll give you kind of a minute to do that. Cool, okay, so let's look at creating our population. So all we really need here, this is pretty simple, is we just want a list of random neural networks. So we have our neural network class that we just made earlier, and we're just going to make a list of kind of 100 neural networks. So that's going to be our initial population. So if we remember, these are all just random, so they're probably going to do pretty badly. But we'll look at how we're going to improve those later. So if we look at the next cell, we're just going to kind of pull out 3 of these random neural networks and see what they look like. So they all kind of have the same structure, and we're feeding them the same input, but they're all giving us quite different outputs here. So this one at the top, this will be random for everybody, but for me, this one's telling, so given that input we saw before, it's telling us to move the paddle upwards, which is obviously a bad decision. This one's telling us to kind of stay in the same position, and this one at the bottom is telling us to move downwards. So kind of purely by chance, this neural network at the bottom is giving us the right answer. So if we evaluated all of these things, we'd find that these 2 here that were giving us the wrong answer will get a low fitness. They'll kind of fail the Pong game, get a bad score. Whereas this one down the bottom, it's going to move the paddle down, block that ball, and get a higher fitness. So in this population, we might, at the end of the run, when we've tested them all, we might decide to cut these top 2 off. We're going to leave them behind, and we're going to go into our new generation with this one down the bottom that actually works. And we'll kind of base our new population off this neural network, changing its values just a little bit to kind of make children of it. So this here is just a function which is kind of going to play our neural networks against each other. So this is going to I'm just going to go through a little brief run through of how this game kind of is played. So in this function, we just have a function for the game. This is already initialized as a helper function. So we're just going to start off our environment, our game, at the top here as custom Pong. And then how this function works is that we can pull observations out of it. So we can pull an observation for the left player and an observation for the right player. So this is what we looked at before. It's kind of how far the ball is away from each paddle, how far the paddles are up on the screen, and whatnot. And then we're going to record a reward for each player. So this is the score they're getting. And then we're going to play the game in steps. So each step, each player picks an action, and the ball is going to move a little bit. So we've just got a loop stepping over them. And at each point in that loop, I'll look at the other one, which isn't filled in. At each point in that loop, each player is going to pick an action. So they're going to use these observations from before, use that get output function that we coded up earlier, and produce what action they think they should do. And then that action is going to get fed back into the game, and the game's going to update, and this loop's kind of going to go around. So what you need to do in this code block is just fill in how these players come up with their action. So if you go back to the neural network code that we looked at before, we have this function get output, which might be useful. So just have a think about how your players can figure out an action based on the current input of the game. So I'll give you a minute or two for that one. So just fill in these 2 lines here, selecting the action. While you guys fill that in, there's a question on, what's this thing called? Minty. So that is, do we have any training set for training the neural network? And the answer to that is no, actually. So there are different ways of training neural networks, and today we're just looking at training these AIs by themselves. So they don't have a training set, they're just kind of learning to play Pong by playing against each other. So we don't tell them what to do at all, apart from telling them their score in the game. Cool, okay, so let's go back to the code. Let's zoom in a little bit more. So our job was to fill in this code picking the action for the left and right players based on these observations that they each make. So what we can do is we can just use this get output function that we got. So what that's going to do is take the observation that we have and just kind of process that through the brain of the AI, if you will, and output the set of numbers at the end, which is the action that they take. So if we run that, then that's all we need to do to kind of evaluate our agents. So you'll notice that they're playing against each other. So the score they will get will be the better one that wins will get a higher score. The one that loses will get the lower score. Cool, so let's check out how well our players do. So if we run this function, this cell here, what it's going to do is it's going to pick us a random network from the population to be on the left side, a random one to be on the right side, and just play the game against each other. So you can see that the left player got a reward of negative 1.46, pretty low, and the right player also didn't do so well, which is kind of expected. These are just random brains at the moment. But the right one did do better. So if we were picking between them, we'd pick the right one. And again, just using a little helper function here, we can actually play the game and see how they do. So you should be able to run this in your notebooks as well. If it's giving you an error, you might have missed the cell where you imported this function, but you can kind of just go scroll up and it should be an import statement for this one here. So it does take a little while. This is run on the cloud, so it can be a little bit slow. If you'd like to test it out afterwards, you can download the code from the GitHub, and that'll be a lot faster because you're running on your actual machine. Just give it a second. And here we can see this game. So we can see why our AIs are doing pretty badly. You know, we've just generated random brains. They don't really know how to play Pong yet, so they're not going to do anything, really. You can see this one just sits at the bottom. This one over here sits to the right and does nothing. So they're obviously just picking that middle action of not moving. You can see when the game kind of first starts, they do move a little bit, but not so well. So our job here is to kind of take this population of bad Pong players and turn it into a good one. So now we kind of need to do this evaluation for all of our population. So we've kind of got this function here to just create a matchup. So it's going to pick 2 players at random out of our population. And then we've got this function that's going to just loop through them all, play them all against each other, and kind of record some average score. So again, we have a little bit of code to fill in here. So you're given this helper function at the top just to select a random opponent. And here, what we're doing is we're taking this population, we're just looping through everything in this population, and you need to write some code which uses that helper function to pick a random opponent, play the game against it, and collect the rewards at the end. So I'll give you guys a few minutes to do that. So remember to use this function here, get opponent index, to kind of get the index of a random opponent in the population which you can play against, and this function up here which we just wrote to play them against each other and get the reward out. Cool. I'm just going to start talking through this one a little bit, but you can keep working as we go. So the first step here is that we want to kind of select the random opponent that we're playing against. So we're going to use that function, the helper function, just to kind of get the index of the opponent in the population that we're going to play against. Then we're just going to pull that out of the population and kind of look at the current rewards we're given. So we're just storing this in a dictionary. And then from there, we've got our opponent. We've got the initial one that we want to test. So we need to play them against each other. So we're using this function that we defined above, the evaluate multi-agent game, to just play the neural network that we're looking at and its opponent and get the rewards back from it. So it's going to tell us how well the neural network we're looking at did and how well the opponent did. And we're going to record both of these in our dictionary. So looking at the entire population, we're going to run this function, and what we're going to get at the end is just kind of a list of scores for all of our members. So they each play some amount of games against random opponents. Kind of, you can think of it like a tournament. They're playing a tournament against each other, and we're just recording where they end up at the end. So if we just look at how that did, it's going to take a little while because we have 100 of these neural networks and they're playing games against a couple of opponents, so we can just keep track of kind of which loop it's on here. And at the end, it's going to print out what the minimum fitness, the worst neural network in the population, what the best one did, and the average fitness of the population as a whole. So here we go. So our worst one did quite badly, about as badly as the ones we saw before. But our best one actually was getting up into the positive scores. So we have one out of these 100 neural networks that's actually doing pretty well, just purely by chance. We didn't tell it how to play or anything. It's just randomly doing well. So if we run this function here to kind of have a look at what it did, we're going to play the best player from that population against each other. So it's going to be on both sides. OK, we'll come back to that one. It's taking a little while. It's taking its time. But we should find that, so that was showing the best player out of the population. So it should be doing actually all right. We saw it had a positive score at the end of the game, which means it's beating kind of its opponents on average. So it should be actually hitting the ball somewhat. If you guys run it yourselves, you should be seeing it kind of moving towards the ball maybe. But it's obviously not good still. This was still a random kind of brain that we created. Here we go, we can see it playing. So they're actually moving around. So you could consider this playing Pong at the moment. And we didn't do any training. This was just purely random, picking the best one. Obviously, they're still missing the ball a lot, but you know, they're pretty good for just random numbers. So what we want to do is kind of make this better. We have 100 of these neural networks. Some of them look like this, and some of them look like the one from before that just did nothing. So what we want to do is kind of combine these good ones with each other to hopefully create children that are kind of even better. So let's look at how we're going to do that. So we need to be able to combine the properties of two neural networks together. So if we have a little look, so up the top here, we have kind of a view of the parameters of each network. So these were the weights of all of the neurons and their biases. So just put them all into a list going across, and kind of cropped it at 4 just to show it off. So you can kind of think of that as the DNA of the neuron, right? It's just a list of numbers of all the parameters, but we can kind of think of it like DNA. And in the real world, how you combine DNA is you just take bits from each parent and kind of combine them together into a new strand of DNA. So that's what we're doing here. So for each number, so for each weight and bias in our neural network, we have a chance of taking the number from the first parent, and we have a chance of taking it from the second parent. And the probability of each is based on how well they did. So here we have the fitness of parent 1, so it got a score of 15. And we've got the fitness of parent 2, which got a score of 5. So parent 1 did better, so you can see it's got a higher likelihood of taking the weights from parent 1. So what that's going to do is it's going to mostly retain the kind of the behaviors of the first parent and just take some of the behaviors of the second parent randomly and kind of combine them together, and we'll see if it's better or not in the next generation. And then what we also have is called mutations. So what a mutation is it's a parameter that isn't from either parent. It's just a random number. And the reason we keep those in, so for one, they happen in real life. Your DNA just gets mutated. And you'd normally think that's a bad thing, right? But actually, it helps us in this case, because what it does is it introduces new behaviors into our system. So just as an example, for humans, for eye color, if you go back thousands of years, humans only had brown eyes. And then one day there was a mutation where humans had blue eyes, and that's introducing new kind of behaviors into what humans can do. So we're doing the same thing here with our Pong players, and these mutations kind of add in new abilities that they have. So when we simulate this, what we have is we've given you a helper function here, try mutate values, that just takes in 3 values. So it takes in a mutated value, which is just a random number, a value from the parent, and a value from the second parent, as well as the fitness of each parent and a mutation rate. So kind of from these 3 numbers, so you can think of that as the first block here. So we have a chance of being this 1 from parent 1, chance of being a 5 from parent 2, or a chance of just being a random mutation. So what this function does is it just kind of rolls the dice and picks for us out of those 3 possibilities. So we're going to use that helper function to kind of, so we're going to build a random neural network here, a child neural network, and then we're just going to go through all of its weights, all of its biases, and use this function to pick a value from the parent, from the left parent, pick a value from the right parent, or pick the mutated value. And what that's going to do is it's going to make this child value kind of inherit behaviors from both parents, as well as some random ones. So we've kind of set up most of the code here. So we're collecting, you can kind of think of this as building the DNA. We're just putting everything into a big list. And then we're just looping over all of the neurons that we have, looping over all of the, that's what you have to do. So for each neuron, you're going to set the bias using this helper function up here. So it's going to pick a bias from either parent or a random one. And then you're going to loop over all the connection weights and do the same thing. So randomly pick a weight from a parent 1, from parent 2, or a mutation. And at the end, we're going to end up with a child that's kind of inheriting properties from both parents. So I'll give you a few minutes to set that one up. So just remember to use this helper function up here, try mutate value. It's going to handle all the probabilities for you. Cool. I'm just going to start working through this. So first, we're setting the bias. So what we do is we just take, so we randomly initialize this child. So the values it already has are kind of the mutated values. It's purely random. So we're going to take its mutated bias. We're going to take the bias from parent 1 and parent 2. And this function is just going to pick one for us at random. And then we're going to set that bias in our child. And then we're going to iterate over all of the connection weights in this neuron and do the same thing. So pick the weight from the first parent, pick it from the second parent, or pick the mutation. And then we're going to end up with this child that's kind of a mixture of both parents. So let's have a look at that. So we're going to take our population, and we're going to pick out the one that did the best and the one that did the second best, and then we're going to combine them to this new child network and see how well it does. So hopefully it's going to inherit the properties, the good properties from both of the parents and do better. But since this is random, maybe it will inherit bad properties and do badly. It's up to chance. So if we have a look at the game, we can see we are probably in the bad case. It's not really doing anything. So this is kind of the difficulty of genetic algorithms, is you're not guaranteed a good result. Everything's random. You could take the best two parents, inherit properties from both of them, and just get something that does nothing. So what we have to do is we just have to run this process a whole bunch, right? On Earth, evolution takes hundreds of years. We have to run this process for generations and generations to kind of build up these good properties. So that's what we're going to do here. We're going to do this child process on the whole population. So if we scroll down here, we have this class, the population class that we made earlier. We've got a helper function for just picking random parents. And we're going to fill in this function to create a new generation based on our current one. So what we're going to do is we're going to retain 25% of the current one. So we're going to retain the best 25 neural networks that we have. And then we're going to fill in the rest of the generation with children. So we're just going to randomly pick two parents, combine them, make a neural network based on those ones. So here is our loop for that one. So we're just filling in the rest of the population. We're going to select a parent 1 using this helper function up here, select random parent. We're going to select parent 2, and then we're going to create a child from it and add it into the population. So this one should be pretty straightforward. We're just going to use this helper function here. So parent 1, we're just going to select a random one from our list of 25 that we're retaining. Going to do the same thing for parent 2, just selecting a random one from these retained ones. And then we are going to create a child based on those ones. So that's using the create child function that we just looked at. So we're going to do something like that. So we're passing in some mutation rate. So you can change this up in your code if you want. I think we set it pretty low, just 1%. So that means every number has a 1% chance of just being random, not taken from either parent. You can bump that up, put it down as you like. There's kind of benefits to both. And then we're just going to add this child to this new generation. And at the end, you can say we're replacing the current population with this next generation. So let's run that one. And let's see it in action. Boop. In the right document. So what we're doing here is we're taking this population that we had before, the previous purely random one, and we're creating a new generation from it. Cool, and then we're just going to test this one and see if it got any better. So this is using the same code that we had before, the tournament style thing, just playing them all against each other. So if you remember what the old population got, I think our maximum fitness was 0.05. So hopefully we're going to do better than that. Cool, so we did. So if you look at the maximum population now, the best one was getting a score of 0.36. So one of these children that we had, that we just made, is doing better than any of the best ones from the previous population. So we've learned something. And if we go ahead and show this one, again, we'll have to wait, but well, we should see it doing better. So this was kind of evolution over one generation, right? And we all know evolution doesn't really occur over one generation, so we're not really expecting a good Pong player after one generation. What we really need to do is run this process over many, many generations. So if you scroll down to the next cell, this one here, that's just what that's doing. So it's running the same process that we just saw over 10 generations here. You can bump that up. 10 still isn't very many, but we need to kind of finish the code running in this course, in this workshop. So if you scroll down here, you'll have to, there's some more to fill in. So there's just 2 lines here. So we have that function that evaluates the population, and then we have the function that creates a new population, and we just do that in a loop. That's all we're doing. We're creating a new generation, evaluating it, creating a new generation, evaluating it, keeping around the best ones every time. So if you go ahead, and you can probably start working on the code here while the last one's running, just recording those 2 from before. So I'll give you a minute or 2 just to think about. So this should be pretty easy. It's just functions we've already looked at, just how we put them together to do it in a loop. Cool, yeah, so this one finished. So this was our 2nd generation, and you can see it's actually, you could probably call this playing Pong now. So after only 2 generations, we kind of properly learned how to play Pong. So it's not doing too well, and you can see it's kind of just cheating by going up and down based on where the ball is, but that's all Pong really is, right? So let's go ahead and train it for more. So that was 2 generations. We're going to give it 10. 10's probably still not very good, so in your code, if you run this, you can try more. You can also try more members in the population. That will give you like more chance of finding better ones every time. But it's going to be a little slow to run, so don't set it to anything crazy. So we're going to set it to 10 and set that going. So you see down here, it's going to be, we should go through what the code was. So we just need to use that evaluate population function to evaluate a population and then create a new generation. So that's all. So that loop is pretty simple. Yeah, so we're going to set that one going. It's going to take a while, but when we come back later, maybe 5 minutes, we'll have trained 10 generations of these things, and I'll be doing pretty good. So let's change tack a little bit and move away from Pong to something else that we can use. So this approach that we've just talked about, evolution of neural networks, is pretty general, right? You can kind of think that the real world does it too. So that evolved animals, things like that, not just Pong players. So we can use the same process to kind of play, you could probably play any game that you wanted, simulate lots of things. So we're going to look at a little bit more of a natural simulation and try and train this neural network to walk, like maybe real biology neural networks do. So first I'm going to give you a little demo again. So scenario is we have this little guy with some legs, and we need to get him to walk. So this is me just playing it. It's like QWOP, if you guys have ever played that. And it's really hard. You're controlling kind of 4 joints at once, trying to get this guy to walk. And it's hard. I can't do it as a human. This is something that I don't know how to get this guy to walk. But we're going to train an AI to do it much better than me. So this is on the GitHub if you guys want to try it yourself. But what we're going to do is we're going to train an AI that learns to walk by itself. So this is showing the different generations that we're going to go through. And you kind of see that each generation, it's learning a little bit more. So this guy actually kind of walks a little bit. But if you watch it, you'll see that it's actually improving over time. And you can kind of see the behaviors go from generation to generation as we're retaining those best neural networks. So this guy's actually doing pretty well after only a few generations, which is surprising. Cool, so this is the next generation, and you can see that he's kind of got the same behaviors. So it's taken the best one from the previous generation, kind of made a child that's doing basically the same thing. So let's go back to our code. And if you just scroll down in the document, so we're still training our Pong games. This is up here. We're on generation 3 at the moment, and we can see that it is improving. So we started at negative 0.9 score, 0.5, 0.3, so we're getting better over time. So we'll leave that to train. And this guy's going to keep popping up there. So let's just have a look at the walker while we wait. So this is, again, just a little demo. So we're just using the same neural network class that we used before for the Pong game. It's exactly the same code that you coded up previously. And here we're just loading in kind of a pre-trained model that I've trained. So you can see all of this. The only thing that's in here is just the values for the bias and weights. This guy's looking a little different. So you can save your AIs just as a file, like a text file. And all it is these numbers that go in the weights and biases of the neurons. So we can't run this code at the moment because the previous one's still running. But we'd just kind of see, we can still see the video. So this was the well-trained, kind of the pre-trained model. And this was probably after 100 generations or so. And he's learned to walk or run pretty naturally. So this is inspired by a biological system, and it can kind of learn these quite complex behaviors. So we're going to stop this one. And this is what the neural network for the walker looks like. It's the same structure that we saw before. Just in this case, we have 4 outputs. So in Pong, we had 3, move up, stay still, move down. Here we've got 4, just controlling each of these kind of 4 leg segments, how much rotation they have. And we've got much more inputs. So here we're simulating the walker actually be able to see. So when you watch it, you can see these little red lines kind of shooting out of his face. And that's actually like him scanning the terrain, like he has little eyeballs looking at the ground. So that's his input, like what he actually sees and feels from his legs. So we've got quite a few inputs here, but it's the same structure. It's still just a list of numbers. We can put it in there. And if we look at the code here, again, there's some code to fill in once our Pong guy finishes playing. But it's actually pretty much exactly the same code as for Pong. The only difference here, so here we're just writing a function to evaluate how these guys are walking. And the only difference here is now we only have one thing before. So before we were playing the Pong agents against each other. So we had kind of a left input and a right input, and they were both taking action. This is going to be the exact same code, just there's one of them. So we have one observation that it's making, and we're just selecting one action. And then again, we have code we create a population of these walkers. We have a function that just loops over them and evaluates them all. So before in the Pong, it was kind of a tournament style thing. And this one, it's a lot simpler. We just take these walkers, put them on the field, and tell them to walk forwards, and we record how far they went. That's all we need to evaluate these guys. And then we just have the same training loop as before. We evaluate the population we have. We create a new generation, evaluate the population, new generation. And this new generation is the same function we used before in Pong. And we can train these walker guys. So even though this is an entirely different, this is kind of a less well-trained one, even though it's an entirely different situation, our neural network is capable enough to learn Pong and walking depending on how you train it. It obviously can't learn both at the same time, but if you created a big enough network, it possibly could. So still waiting for see if our Pong player is finished. So we trained for 10 generations, and the maximum Pong player had a score of 0.63. and let's see how this does. So we still have to, so we're going to play the best two after those 10 generations against each other and just see how they did. Cool, and so while we're waiting for that, we're just going to go do a little quiz. So when we look back at these 10 generations, do we expect the average population to improve over time? Does anyone have an answer for that one? I can see a couple of nodding heads. A hoodie. We're giving away a hoodie for this one. So does anyone have anyone will put their hand up and put an answer worthy of a hoodie? Yep.
Yes, I'd expect the average population fitness to improve over time because you're culling the bottom 75% every generation.
Yep. So that is a good answer if we're looking at the walkers. So the walkers, it's one agent. So it should get better over time, right? It's training to walk.
I was thinking of Pong.
Yeah, so in Pong, we have a slightly different situation because we're playing them against each other in this tournament style thing. So can anyone think why we might not see? So if we look at these last generations, we can actually see it went down from 8 to 9. Does anyone have an explanation for that?
Could particular brains develop strategies that beats others so that causes others to do worse, decreasing the average while only some benefit?
Yes, I think we can give that a hoodie answer, right? I think that pretty much answered it. So for the walker, we would expect the fitness to go up because these things are just walking further and further. But for the Pong, they're playing against each other. So since we're taking the best members of this population to create the new generation, we can kind of think of it like the right side's getting better over time, but the left side's also getting better over time. So they could just be getting better and better, but since they're playing against a harder opponent, their score might not go up. So that's actually what we see. You could train this thing for 100 generations and still get a score of 0.63, but at the end, they'll be kind of expert Pong players just, whacking across the board against each other, and neither of them is really beating the other one. So that was kind of a trick question there. I think your answer was good, but just in this situation. So I think you've won 2 hoodies. So maybe we'll give you a hoodie. So let's see. Yeah, we finished recording this. So this was our players after 10 generations. And you can see they're actually playing Pong now, right? Like they're hitting it back and forward. This guy on the left still losing health, but he's losing health because his opponent's pretty good, right? So he's doing the right moves. Yeah, so these guys are actually playing Pong. So we've trained Pong players in 10 generations of populations. So yeah, they can play Pong. You could play Pong against this guy, and you might win, you might lose. I'd probably lose. I'm not very good at it. Yeah, does anyone have any questions about that? So that's the end of the Pong section. We've trained Pong players. Yep.
Is it possible to work out efficient ways of developing the AI such that they don't survive to any sort of local maxima? That sometimes might develop.
Yep. So yeah, so that's exactly what people look at with these genetic algorithms. So we kind of touched on it before. So genetic algorithms aren't the only ways to train these things, but they are a way. And you're exactly right. Like these populations will kind of fall into areas where they can't learn so well. So one way that might happen is if you suddenly just got like one member that was doing some really weird strategy, like just going to the bottom and trying to like whack it up into the top corner. And your population is kind of going to learn to counter that strategy and only that strategy. So you'll end up with a really weird situation where I actually encountered this when I was kind of developing this. They just sit in the bottom and like do a 45 degrees back and forth forever. So there's lots of genetic algorithm kind of tricks to solve that. So mutation is one. The other one is kind of the style of tournaments you play. So you might not just select the best ones, but you might select some of the bottom ones as well, just to kind of introduce a bit more diversity into your population. So there's a whole bunch of things you can do like that, and it is like a area people study for optimizing this. Cool, yeah, so any more questions about the Pong? Yep.
So what's a kind of solution to that kind of back and forth competition? What's the best generation?
Yeah, so kind of like I just said, one of the things is introducing more diversity. So if they're really fixed on one strategy for winning, and you kind of turn up the randomness a bit more, you might randomly get one that does a good counter strategy, right? And then you'll kind of break the monopoly of them all doing the same thing. And another way is you've just got to set the scores right. So it's quite important that you set scores that train the right agents. So it's actually there's quite a bit of thinking involved for these scores here. So they get plus score when they hit the ball back, but they also get negative score over time. And the reason for that is because if you just give them reward for hitting the ball, they'll kind of hit at a really big angle, so it just bounces really slowly across the screen. And the reason for that is they kind of want to extend the game so they don't lose as quickly. So if you can change the reward so it drops over time, they kind of learn that they want to play quick games where they're just kind of whacking it back and forth, if that makes sense. So there's quite a lot of parameters you can tune in how you reward them, because the reward's kind of you telling them what to do and what not to do. So you can kind of adjust the rewards to get them to play how you want them to play. We won't see that in the walking, but the reward we get from the walker is just how far it goes and how fast it goes. So you can see this guy, he's just trained to kind of run down the screen because that's what he's getting reward for. But one of the other devs guys, I think, mentioned that we could train him to jump by giving a reward for how high in the air he gets. And if we kind of train that one using the same network for 100 generations, we wouldn't see behavior like this where he's just running. We'd see him trying to jump in the air as high as possible. So by kind of tuning what rewards you give it, you can get the behavior that you want using exactly the same training methods and exactly the same code. So let's run this for a bit. So again, this is a utility function. It's kind of the same as we saw before, but it's just for displaying a single agent. So this is loading in this saved one. So again, that's kind of the cool thing about these AIs. There's nothing really complicated. It's just a list of numbers. You can just save this as a text file and load it in. That's all it really is. So we're recording this guy. It's actually going to give us the same video here, so it's not very exciting. If we go back to our one running in the background, he's still kind of using that same behavior of like the straight front leg, but he's kind of learned to bend it a little bit, to walk a little bit faster. So he's learning over time. Cool, and this is the pre-trained model again. So he's running, show this network for him, and it's nothing complicated. Remember, we'd have a weight for each of these lines across here and a bias for each of these neurons, but that's all this network is. It's just a list of weights and biases, and we'd code this evaluation function. So again, this is what we saw before. We're just getting the action from passing the agent the observation every step, and we're like stepping the game forward based on that action every time, and then stacking up the reward that we get for every frame. And then this is a code just to go over a population of these walkers, kind of play the game with them, see how far they get, and assign that as their fitness. So we're just looping over all of the members, evaluating the single game, and setting their reward. And then this is just calculating averages over all of the games. And then, again, this is just the function that goes over multiple generations. So we are creating a population at the start, our initial random population. We are evaluating how good it is, creating a new generation based on that in a loop. So this one should run a little quicker. And for this one, we should see the fitness going up over time. So our first walker got a fitness of -92, which isn't very good. That's a negative value, so it's kind of fallen backwards, I guess, a little sad. But our next generation's up to -21, getting better over time. I think we're training 10 generations of these. So the output from this one will just be what we saw here. So that's kind of it for us. We have, look at some conclusions. We looked at how a human brain would play a game. So that was the loop that Liam showed us at the start of taking in observations, processing that through our brain, producing some output. An interesting thing there was that's all numbers, right? Your eyes see something, and that gets converted into electrical signals in your nerves. And those signals are just processed through your brain and go down to your arm. So it's all just kind of mixing and matching those electrical signals in your brain. And we can simulate that with our neural network that we did. So we kind of play Pong well. We needed to train that random neural network to kind of pick the right outputs for a given situation. So for a given set of inputs, we want it to pick one right output. So we use genetic algorithms to kind of go through generations that slowly picked better and better outputs over time until eventually they could play Pong. And then we saw finally that we can use the exact same idea to kind of do a bit more of a biological inspired system and learn how to walk. So yeah, so now it's your turn. So all the code's on the GitHub. It's pretty fun to play with. You can try and change the rewards, maybe try and get this walker guy to jump. That'd be pretty cool. And it's a little bit more interactive on the GitHub. You can actually play games against these Pong agents and things like that. So the GitHub link is here, genetic Pong. So have a look, and yeah, feel free, oops, you got a bit stuck there, to send us any feedback, ask me any questions. Yeah, that's it for us.